I'm just going to give you some oversight, some basic background, some terminology, some framework, so you can go back and then build from. I will send out the PowerPoint so it can be distributed, because I've got notes in places along the way and then note frames as well for some of the components, so don't feel you have to quick
Thank you.
try to write everything down, especially when we get to the technical parts. Because I will go through the technical definitions a little bit, but you can always pull out the important elements and synthesize them down to grade appropriate. You have to see the bigger picture to really see how the pieces fit together. Okay, so let's get started before we lose too many people to whatever. What did we come up with this morning for what, or an informal definition of transformational geometry? I'm not even going to give a formal one, but what did we come up with for an informal conceptualization of transformational geometry?
Moving shapes.
Moving shapes? Okay. So it's in a sense, it's kind of more dynamic. It's kind of a dynamic geometry. Think about Euclidean geometry, compass and straight edge. That's kind of
Stationary.
Static. It's there, whereas transformational has a sense of movement to it. We're also going to find out it's very connected to advanced mathematical ideas, and I'll talk a little more about that when we get to that part. But it is kind of a motion sense, because you're picking, in a sense, we're going to pick an object physically. If you think about physically, you're picking an object up and moving it to another location. It's just we restrict what are your legal moves in some sense. Now, it's broader than that, but for transformational geometry, we have a determined set of, okay, legal moves.
The translation.
Well, we'll define those a little bit.
Oh, I thought you were asking what they were.
No, I just said we have them.
Yes, we do.
And we'll put those together. There we go. How to wait for the machine now. Okay, so a little bit of history. Anyone heard of a person called Euclid?
No.
Yeah, I have no idea. The elements. Euclid was kind of the first person to try to put geometry into a single synthesized package, an organized package, taking all the knowledge that was available at the time he wrote the elements and trying to put it together. There are parts he probably created, but most of it he got from other people and just figured out, how do I put it in some sort of structural order? How do I set this thing up in a systematic fashion? Early precursors of what we do today, what we call axiomatic systems. Believe it or not, though, he actually also brought in a little transformational geometry. Well, it wasn't called that back then. Very early on, when he was trying to prove what we now call side-angle-side congruency, he was in essence using something called he didn't call it this, but we eventually named it, the principle of superposition, which is really a transformational geometry idea. He was basically saying, I can pick this triangle up and put it down on another one and match the corresponding parts up to show that they are, if I have the side, the included angle, and the second side, those match up and the triangles are congruent. Unfortunately, there's a small flaw in the logic to that point. Historically, what happens when you pick what could happen when you pick an object up? It could be distorted. A shift could occur in the process of moving down. He didn't have a way when people went back and critiqued it, there wasn't a way to ensure that when you picked this object up and moved it, that it was locked in position. So it remained. If you could have picked it up, like silly putty or something, move it around, put it back on. Okay, anything can be done. Okay, it turned out we could fix that, but that was an underlying critique of why his ideas of transformational geometry didn't really go very far. He didn't use it that often, but he used it some. So that idea got set on the back burner for a long time. Eventually, until about 1827, Mobius of Mobius band fame, basically started to flesh out the idea of what we now know as transformational geometry. So we're talking span from Euclid all the way up to Mobius before the idea started coming back. And he started giving the idea of compositions of motions in the plane. So he kind of defined what we mean by motion in the plane, generically, and what we need to put them together, composition. He started fleshing that idea, but it was still really loose and not put together. It wasn't until Klein, Felix Klein, mid to late 1800s, really developed the framework for what we now know as transformational geometry. And it was through his study of something called invariant spaces. He was looking at a much bigger, broader topic and heavy duty into abstract algebra. But out of that work came the framework for all the pieces for transformational geometry. He got all the theory kind of lined up, formally defined how we can deal with the principle of superposition and define it formally so we know we pick the object up and move it. What are the legal moves you can use so that you know when you pick it up you're not going to be altering it to fit on the other one, and setting those ideas up. Thus, Klein in many cases is kind of considered the father of modern transformational geometry. So if you look at it, transformational geometry has only been around for about 150 years as an idea. The ideas have kind of been around, but the formalization of it and how we think about it today. And I'll talk a little more about it later, some of those connections. The one thing you have to keep in mind is Euclidean geometry, transformational geometry are very much related. They go hand in hand. But they have different thought processes. You have to visualize and think about things a little different when you're in Euclidean geometry versus when you look at the same thing from a transformational point of view. It's much more visual. It's a different mindset. My students from the spring in my secondary math geometry class, we finally got a little further in transformational geometry than we usually did. They really hit it home when they decide you really do have to think differently in a transformational mode from a Euclidean mode. They overlap, but how you go about writing proofs and thinking about setting up proofs and descriptions, you have to have a slightly different mindset because you're going from a static scenario to that dynamic one. If you think back, GSP, Geometry Sketchpad, a lot of the activities, if you follow the direct ones from the publishers and stuff, they use transformational geometry ideas to build the diagrams. But yet when you try to write the proofs and they ask the questions about them, the questions are all Euclidean based. They're not asking anything in terms of the framework from transformational geometry, but yet they're using those techniques to make the pictures and draw them. So there's a disconnect between what's happening with the action on the screen and the description versus what's happening mathematically. Really, the questions should be framed in a transformational point of view. That's one thing about transformational geometry is going to hopefully switch that, but it's going to be an override. Because most of the time transformational geometry ideas are embedded in Euclidean. So you define transformational geometry ideas in terms of Euclidean ideas. With the Common Core, what are we doing? We're moving transformations to the front, which means we've got to redefine, reset everything to the language of transformational geometries and build into Euclidean. So we also have a different mindset there as well. Now, talk a little bit about that later. That kind of gives an oversight. But that's a little bit of the history. Okay, basic background. Whoops, get the right key, it'll be helpful. Okay, a couple of technical definitions, some of which you may be familiar with. I'm not going to necessarily read everything, but transformational geometry is built around transformations of the plane. Very generic. This is a very nondescript because there's lots and lots and lots of transformations of the plane. Not all of them will end up being in transformational geometry, though. But this is the basic idea. Don't get too hung up over it. But a transformation of the plane, I'm just going to call it capital T, to name it, so I don't have to keep saying the full word, is a one-to-one and onto function, or mapping, that associates each point P in some plane with some other point P prime in that same plane. So basically, T of capital P equals capital P prime, or T evaluated at capital P equals P prime. Now, what are you noticing right there? Functions. Transformational geometry is built off the notion of functions, which means we're going to now connect geometry to algebra. So we get that deeper end connection idea going on. Transformational geometry is built off the notion of function, though we don't call them functions in geometry, we call them mappings. Is really what they're usually called, but I put the word function in here because that's the nice connector. But we still have evaluations. It's just instead of numbers or expressions, we're using geometric objects along the way. And then we have this notion of one-to-one and onto function. I'm not going to get into the technical definitions unless anyone really wants to, but what that really forces us to have is we can, and The kids really don't have to have it, but what it allows for in the theory is that we can come up with inverse functions. So you can undo something and basically reverse the process. We want to be able to reverse processes. The other thing, it also allows us to put the compositions together in a nice way. We have a one-to-one and onto function. You compose two of them, you get a one-to-one and onto function. So composition of a transformation is a transformation. That's a nice property to have. If we didn't have those conditions, we may lose some of that, and we need the structure. But the one-to-one and onto basically really gets us the fact that we can then have inverse functions. So we can undo something and have it make sense and be unique. So we get that uniqueness aspect of it. That's why we need this. We're going to get it very far away from one-to-one and onto, but you need to have that framework underneath that's what's holding it together and makes it work nice for us. And then a couple of terms. Point P is called the preimage of P prime, and P prime is called the image of P. So the thing you start with is preimage, where you end up is the image. Most of you are kind of familiar with that. It's just for completeness sake, if you're not familiar with it. But keeping track of it. Be real useful, and when we're doing things more complicated, where you're doing a sequence of things, you want to know where was the preimage of the whole thing, where's the image of the whole thing, so you can keep track of where those are. Okay, so I'm done talking for a little bit. It's time to do some explorations. Now, this is a packet of things, and I've got to get them separated appropriately. Got 2 green sheets there.
Can we help you, Tom?
Pardon?
Can we help?
Sure, if you want to. And I can talk. Basically, if you go down to the green sheet.
Okay.
Packets are separated green sheet. You've already seen some of these activities. These came out of the Patty Paper book. There are 2 versions of every activity in that book. There's the open investigation version and a guided investigation version. So the first part here, you're going to have seen the activities a little bit, but you're going to see the guided version this time. So what we're going to do is we'll get these passed out. You can work through them. Basically, we're going to see how well people follow directions. Bullet point 1, you're supposed to do some things. I'm going to pass out another packet. You're supposed to do the first 9